Here we have a rather badly drawn diagram of the Earth. And before we can talk about all the interesting stuff like continental drift and tectonic plates, we need to first understand what all of these layers actually are. And so hopefully first you realise that this is what the Earth would look like if we took a knife and we cut it right down the middle. This is obviously not what the Earth looks like if we take a photo of it from space. If we cut it down the middle and we can see all the layers which make up the Earth, it will look something like this. And so if we start from outside, our first layer is known as the atmosphere. Now, most of the atmosphere lies within around about 10 kilometers of the Earth's surface, and it includes all the air that we breathe in all the time on a regular basis. The atmosphere actually does extend further than this to around about 100 kilometers above the Earth's surface, but most of the material within the atmosphere lies in the first 10 kilometers. Now, the most abundant element which makes up the atmosphere is nitrogen gas. So the atmosphere contains around about 78% nitrogen, I'm just going to write N2, and also around about 21% oxygen. 21% oxygen. Obviously, if you add those together, that's about 99% of the atmosphere. So the remaining 1% is going to be all your other trace gases, including the noble gases. Obviously, one big one is going to be carbon dioxide. You're going to have methane in there, but the majority of all the material in the atmosphere is actually nitrogen and oxygen. Then if we look into the solid part of the Earth, our outer layer is of course known as the Earth's crust. Okay, the Earth's crust varies quite drastically in how thick it is, because underneath the oceans you have a thin layer of crust which is around about 5 kilometers-ish. Whereas under the continent, so the land where we are at the moment, well, the crust is thicker there because we are sitting on solid, and that is around about, or up to about 50 kilometers, between 35 and 50 kilometers, and you've got an average, if you like, because obviously most of the Earth is covered in ocean, we have an average, so an average of 6 kilometers thickness. That is because most of the Earth is water, but under the land, under the continents, all the countries where we are at the moment, the crust is actually going to be quite a lot thicker there. So I'll put around about, let's say 40 kilometers under land. Next, if we look in slightly deeper into this yellow part here, we have what is known as the Earth's mantle. Sorry about the handwriting, M-A-N-T-L-E. The mantle. Now the mantle is way thicker, it's approximately 3,000 kilometers thick. And it's pretty much a solid. We say it acts as a solid. And the reason we say that is because it does flow. It does flow, and obviously that is characteristic of fluids, so liquids and gases, they flow, but the mantle will flow very slightly, and that is the reason for something known as continental drift. That is why the continents can actually move, because the mantle will slowly flow, and so the crust which is sitting on top of it will end up actually moving. So it acts as a solid, but it does flow in some places. And so we then have the Earth's core, and the Earth's core is split up into two sections. And first we have the outer core, which is this orange section down here. Now the core, the outer and the inner core, is almost entirely made of nickel and iron. So nickel plus iron, and the outer core is actually a liquid. So the outer core is a liquid and it is runny, it will flow quite a lot, whereas the mantle obviously behaves like a solid, but it will flow, which gives it some liquid characteristic as well. And so lastly, of course, we have the inner core. The inner core, which is a solid. And that is made of nickel and iron as well, but it's mostly iron. So it's mostly iron. And you might think, well, if the mantle is pretty much a solid and the inner core is a solid, why is the outer core a liquid? Well, it's all got to do with temperature. As you go towards the Earth's core, you're going to get hotter and hotter and hotter. But then why isn't the inner core completely a liquid? Well, it's made of slightly different things than the outer core, and you're also at a massively high pressure once you get inside to the middle. So that is also going to cause different characteristics from a liquid to a solid. And so they are the different layers of the Earth. Make sure you do take time to learn these. We probably went through that pretty fast, so feel free to rewind. Make sure you get all of this down because it is very important and will be tested on. Okay, so moving on now. Having mentioned continental drift already, let's take a look at that in a little more detail. So here we have a map, or a general map of the Earth. One thing you might notice is that if we take a look at South America, and the east coast of South America, which is here, that looks remarkably similar to the west coast of Africa, drawn here. If we were to take off South America and we were to move it this way, it would be almost an exact fit into this groove here on Africa. Now that's pretty fishy, and it suggests that maybe at some point this part of America was actually joined to this part of Africa. Now obviously this could just be a coincidence, but scientists looked into it a little deeper and they found that the layers of rocks on both these coasts, so on South America and Africa, they have been built up in the same layers. So the rocks underneath have the same sequence of rock in which they've been built. And this obviously suggests that they've also come from the same place. Because if you go all around the Earth on different coastlines, there will be different types of rock forming layers. And if you have exactly the same sequence, then that is quite a big coincidence. And finally, even more evidence, if you look into those layers of rock, if you dig down deep enough, you find that the same types of reptiles and the same types of plants actually came from the west coast of Africa and the east coast of South America. So you've got, back in time, a long way back in time, you've got the same species coming from the same place and the same types of rock, and these two continents fit together. That is a lot of evidence which suggests that there is something more than just pure coincidence happening here. And so scientists now believe that they can explain this by saying that these two pieces of land here were actually once joined as a single land mass. And we now suggest that these pieces of land have been moving apart very slowly over thousands and thousands of years, so over a long time, and this has caused them to become separate, and now we call them two separate continents. Now, the structure that's allowed them to do this actually comes from the crust and the uppermost part of the mantle. Now, if we take a look back at our diagram, the crust, so this part in brown here, and the uppermost part of the mantle, so this large yellow bit here, they are actually cracked, and therefore we have separate pieces of mass on the Earth which are sort of independent of each other. And so those large pieces are known as tectonic plates. Tectonic plates. So tectonic plates are large pieces of land which are separate, large pieces of the Earth's crust and the uppermost part of the mantle, which are able to move independently of each other. So now we've established the tectonic plates can move. What actually causes them to move? Well, it actually lies in the phenomenon known as a convection current. Now, you've probably heard about that when you've studied physics. It happens in fluids, so liquids and gases, and it's where hot material will rise and cool material will sink. And this creates a movement of material, which is the reason why we have wind, especially at the coast, when you've got the ocean there, which is going to affect the temperature and cause changes in the convection current, and various other things as well. And so let's take a look again at a diagram of the Earth without the labels on it. So what's actually happening here is that the Earth's core, so the inner core here, but more importantly the outer core, I'll show that in a different colour. The outer core, which is here, this is extremely hot. Now the mantle above it is going to be made out of various different rocks, and as they approach the core, here, this is where you have the hottest temperature. And so here, the rocks and different minerals in the mantle will actually be heated and they will rise up. And so they'll rise up through the mantle to the top. And so because the hot rock is rising up, after being heated, it will make its way to the top, And so as it hits the top, it's not going to make its way through the crust most of the time, but it is going to instead be pushed sideways, like this. And so now as the rocks are moving sideways, they're also taking with them the tectonic plates, because they are parts of the upper mantle and the crust. And so the tectonic plates themselves are going to be moving as well. Now, as the rock is moving this way and this way, because it's now not anywhere near the Earth's core, it's going to start cooling down, and eventually, when it's cool enough, it's going to sink again. So we're going to get the rock sinking back down, like this. And the cycle is complete there, because it's going to be happening again and again. Here, now it's back close to the Earth's core, it's going to heat up again, and it's going to rise again, and so on and so on. And because this is happening very slowly, but it is happening all the time, we are getting very slow movement of the tectonic plates, which are sitting at the top of the mantle and on the Earth's crust. And finally, one important thing which is actually contributing to the release of all this heat from the Earth's core is the decay of radioactive material. And radioactive decay releases a lot of energy in the form of heat. Now, the guy who proposed this theory of continental drift was called Alfred Wegener. And this was in 1915. So he proposed this theory, whereas common belief was that the Earth's surface was almost like the top layer of hot custard, in the sense that when the Earth's surface cooled down, it began to shrink and become all shriveled, just like the top of a pot of custard does. So if the rock became cooler and it shriveled up, then that would give rise to creases and eventually, of course, mountain ranges. Now, there was another chap called Edward Suess. Forgive me if I've pronounced that wrong. Suess, spelt like this. Edward Suess. He said that the reason why these two shapes complement each other is because in history there was a piece of land in between here. So like this would all be land as well. And he said that this piece of land broke off and sunk, and that is why we now have a gap in which we have two complementary shapes. And so Wegener actually, his theory really does go against this. Problem is, and in 1915, he couldn't actually explain how or why his theory was actually true. So he suggested that the continents were moving apart, but he couldn't explain how the process was actually happening. And so it took almost 50 years for scientists to actually find evidence for his theory, and which is now accepted. And the evidence comes from seafloor trenches. So seafloor trenches. And we can see that those points under the ocean are actually moving apart, and molten rock is spewing out. And because we can see that those trenches are moving apart, that is good evidence to say that the Earth's crust is moving apart, and plate tectonics is the explanation for this. Now, you've probably heard about plate tectonics in the sense of earthquakes and volcanoes and affecting when and how a volcanic eruption is going to occur and things like that. Now, what's happening here is, let's say that we have two imaginary plates. Let's pretend these are tectonic plates, okay? They're quite close to each other, and they can look something like that. These will be massive. They're not just tiny little plates. These are huge. So, for example, one plate covers more than the entire of Africa. But let's pretend for a second that this plate on the right is moving very slowly, and then crack, it hits the plate on the left. Here, what we have is two plates colliding with each other. And this will cause a massive amount of stress and a massive amount of force to build up, because these plates are so big. Now, this huge amount of stress could cause the Earth here to sort of give, and therefore the forces driving into each other will cause the Earth to actually fold upwards or push itself upwards. So we'd have two pieces that have come together like this, and as they've hit each other, they forced each other upwards like that. And because these are so massive, eventually this will happen, and it will push up and up and up and up, and you'll eventually get what is a mountain. So this can cause mountain ranges to form. What could also happen is, if these are rubbing each other or they're on top of each other, if they slip past each other, in a sudden sort of jolting movement, because the Earth is actually moving there, that is what is known as an earthquake. A sudden movement of the Earth will cause shaking of all the landmass, and that is an earthquake. And so when two plates actually do collide, or they come together, or slip past each other, that is when we can get earthquakes. Now, for obvious reasons, this is actually quite hard for us to predict, because we don't know when the plates are going to rub together. Even if they are coming together, we don't know how violent the movement is going to be. We don't know whether they are going to force the land upwards or whether they're going to slip past each other. So it's quite difficult to accurately predict an earthquake or a volcanic eruption occurring. However, we can actually look at infrared cameras, because when two plates come together like this, you'll get a build-up of heat. Because if you rub your hands together, friction will cause your hands to heat up. This is happening on a massive scale here, and so we can detect heat being given off here. This means that we could get an earthquake. We could also get a volcanic eruption, because if there is a lot of heated rock at the surface, it could burst out of the Earth's crust, and that is a volcanic eruption. And so we can actually make some predictions on eruptions and on earthquakes. As technology improves, we will get better and better at this, but it's not a precise science at the moment, and that is why we can get shock earthquakes, shock volcanic eruptions, and other things like that. Now, it's important to realise that the shape of our land masses, so our continents and everything else, is not the only thing that has changed during the course of the Earth's lifetime. It is pretty much accepted that the atmosphere of the early Earth, so billions of years ago, was very different to what it is today. And so we'll outline a few ways in which it is different. So scientists believe that the Earth was actually formed around 4.5 billion years ago. So 4.5 billion years. That's 4.5 thousand million. So it's a very long time ago, and it's thought that originally the Earth was covered in volcanoes and they were erupting all the time, and gases were being given off into the atmosphere, and obviously it was a very harsh environment to live in. And that's why there was no life at the start of Earth, because this environment doesn't really allow things to grow and settle. Now, there are various different theories actually about the exact sort of components of the early atmosphere. No one can ever categorically prove it, because obviously no one was alive 4.5 billion years ago. But one of the main theories is that the gases being given off included lots of carbon dioxide, some water vapour and nitrogen gas, which were being given off obviously into the air. Now, it's thought that over time the Earth was gradually cooling down. It was becoming a less violent sort of environment, and the Earth was cooling down. As this happened, of course, if the temperature went below 100 degrees Celsius, the water vapour would turn into liquid water. This would fall as a lot of rain, so a high amount of rain, and it's thought that it collected in grooves within the Earth and eventually formed what we now obviously see as the oceans. And so this sort of stabilised, and most of the water was found in the liquid form as we see it now, and therefore most of the air was made up of carbon dioxide and nitrogen gas. Note there that there's barely any oxygen. I haven't mentioned oxygen because there is thought to have been almost no oxygen in the atmosphere, as this would come later. So this created a stable environment until life formed. So around 3.5 billion, or more correctly 3.4 billion years ago, so 3.4 billion years ago, life is thought to have started. And of course, to start with, all we had was our simple bacteria floating around, and these were the sort of early life forms. Bacteria were able to survive because they're very simple organisms, and they were able to use the chemicals that were present on the Earth and in the atmosphere, whether that be the nitrogen or whether that be the carbon dioxide, in order to survive and create nutrients. Now, it's thought that over time, these bacteria evolved into slightly more complex bacteria and also algae. So I've drawn these in green, and so these bacteria and also the algae are able to carry out a process known as photosynthesis. Obviously, we now know that photosynthesis is the main sort of defining feature of the plants as well. Plants now, especially green plants, carry out photosynthesis all the time to produce carbon compounds, mainly sugars, for themselves. So we get photosynthesis occurring, and one of the waste products of photosynthesis is oxygen. So these organisms were releasing oxygen into the atmosphere, whereas before there was little to no oxygen in the atmosphere originally. And so the algae and the bacteria were doing fine. They were photosynthesizing, releasing oxygen into the atmosphere, and this allowed for the evolution of other types of animals, or other types of organisms, sorry, which will eventually include animals, but first it's going to give rise to more complex forms of algae and plants, so green plants. So most of the algae and the bacteria, originally they would have been in the oceans. And then once we formed a larger variety of different plants and bacteria and algae, they were then able to colonize the solid surface of the earth, so the land. And now obviously we see plants all over the earth, and they are able to survive in the land, and we also have sea plants as well. And so these were contributing more and more and more to the release of oxygen, which led to the evolution of organisms who could actually use that oxygen in order to carry out their chemical processes. And that is obviously respiration is the main one. And that will have led to more complex aerobic organisms. Aerobic means using oxygen, which eventually will of course lead to animals. So we're going from simple organisms to more complex organisms. And as more and more oxygen is being released into the atmosphere, this is actually detrimental to the first forms of life which are on the Earth. And that is, we can still see the evidence of that today, because many forms of bacteria, they can survive perfectly without oxygen. When there is oxygen, a lot of them can still survive, but as you get more and more and more, the level of oxygen increases. This actually becomes toxic to a lot of bacteria because they don't like oxygen, they don't use oxygen. They can put up with some of it, but as the levels of oxygen increase, they will actually start to die. Oxygen is toxic to them. And so therefore, many of the early forms of life will have started to die out. They could become extinct, or they could move to places on the Earth which are harsher environments, if you like, which are void of oxygen. And so that is a very general sort of summary of how it is thought that life came about on Earth. Now, in order to recreate this, if you like, obviously a much more simplified version, there is an experiment known as the Miller-Urey experiment. And this would attempt to form the biological molecules which we need for life. One of those main molecules is an amino acid. And therefore, they want to see whether the conditions of the early Earth, so the harsher conditions of the early Earth, could lead to the molecules we now see today. If you are taking the foundation course, then do not worry about this experiment. Feel free to stop the video now, because this is actually slightly higher level stuff, and you're only expected to know this experiment if you are taking the higher paper. And so the Miller-Urey experiment included 4 of the main components of the air in the early Earth. So we had water vapour, so H2O, we had methane, CH4, we had ammonia, NH3, and hydrogen gas, which is H2. If we take these gases and we put them all into the same container, then nothing really will happen. And so that's not very useful, but in order to recreate the atmosphere in the early Earth, you think, well, it was quite a violent atmosphere. Even now, of course, we'll always see thunderstorms occurring somewhere, which includes a massive amount of energy in the lightning. And so to recreate this, Miller and Urey created a high voltage spark using electrodes, which would provide a high amount of energy similar to what you would get from a lightning bolt, and therefore they would be able to see whether this could force these gases to actually react. So here let's have a look and talk through the equipment that Miller and Urey actually used in the experiment. So as I mentioned before, we have our container which has water, methane, ammonia and hydrogen gas. We have these here these are actually the electrodes. So here and here we have electrodes. Okay, all these are doing is they are creating that high voltage electrical spark, which is meant to mimic the energy produced by lightning, and therefore will show whether this can cause reactions to occur. And so remember we said that after a while the Earth began to actually cool down, so the environment became slightly less harsh. That is what we're recreating here. So this is known as a condenser. And what we're doing is we're providing cold water in here, not to the mixture itself, but to this condenser in order to cool the mixture down. And so the mixture will travel this way, and after it's been cooled down, then we are going to get a liquid formed. And so down here, this is what is known as a trap. And here we would take samples, so this is called a sampling probe. Sample probe. And here this allowed us to actually take samples and analyse what we had produced in terms of chemicals in this liquid water, or the liquid mixture which included water. And one result, I'm going to do the results in green, one result is that they found organic compounds. So organic compounds were found when they tested the mixture which had been produced down here. Those organic compounds were not there to begin with, and therefore chemical reactions must have taken place. And so then moving on here, we had a beaker which was full of water. So this contains water. Okay, and this is in order to mimic the oceans. So we have a large sort of sink of water, if you like. And here, this would be heat. So here we're heating it in order to create water vapor. So just as is happening in the Earth's atmosphere when we evaporate water, heating water here causes evaporation and the gas rises up and goes back round. Here we had another sampling probe. So another sample probe so we could test the components and what is actually chemically inside this water. And here we have a vacuum pump. And this vacuum pump was just to make sure that the circulation was carrying on fully and that we weren't getting things coming in from outside or leaving either. So vacuum pump. And so this simulation was of the early Earth's atmosphere. And what did they actually find? Well, after around about a week, they found that the solution or the mixture was brown. They described it as a brown soup-like mixture. But on chemical analysis, this contained at least 11 amino acids. And they had come completely from chemical reactions because the vacuum hadn't allowed anything in, and we'd started only with four substances, 4 molecules: H2O, methane, ammonia, NH3, and hydrogen gas. So chemical reactions had occurred as a result of our simulation. Now this was a massive, groundbreaking experiment because it showed that life, coming from just the basic molecules found in the atmosphere, life eventually could form. Amino acids are the basic molecules of proteins. So the basic molecules which make up proteins. Proteins are found in every living organism on the planet, and all of those are made up of amino acids. So the fact that we can produce amino acids like this in a lab shows that this could happen outside a lab. If these conditions were replicated in real life, then we could actually end up with amino acids formed. Now since then, this experiment has been repeated and we've got more advanced methods of detecting different substances, and we've actually found that we can produce way over 20 amino acids via this method. In life, so especially in humans and related organisms, there are 20 amino acids found in our proteins. So that means that we can form more than enough amino acids in order to sustain full life. So that is all well and good, but as with almost every single scientific experiment ever, there are people who disagree. There are people who say that this isn't clear proof. And so what are the flip sides to this? What are the arguments against? So arguments, well, one was that if we have a look at what we started with here, we didn't include oxygen. And we are brought up to believe, and most scientists actually do believe, that most organisms only started evolving, so especially animals and other organisms like that, started evolving when oxygen turned up in the atmosphere. And so the fact that Miller-Urey have left out oxygen from their experiment makes the results inaccurate. So, no oxygen in Miller-Urey experiment. Results, therefore, invalid. Okay, that's one argument again. Now, there are other theories about how life began as well, and one of those, which is quite striking, is that in the year 1969, so in 1969, a meteorite known as the Murchison meteorite landed on Australia. Now, we have analysed the meteorite and its components, and it is actually rich in biological molecules. So it's rich in amino acids. Over 70 amino acids, 70 amino acids were found on this meteorite. And that suggests that perhaps a meteorite could have landed on Earth at some point a long, long time ago, and it could have brought along life with it. So all of us may have actually come from another planet. So that's quite a dramatic theory, but it is one which, from looking at the components of the meteorite, at least, is an acceptable theory, if you like. It's one which deserves consideration. Now, there are many other theories as well, so if you are really interested in the topic, then please do feel free to look those up. I'm not going to go into all of them, but it's important to realise that although the Miller-Urey experiment shows that we can form amino acids from just basic molecules which are not organic, it does, however, have its disadvantages. There are people who doubt it, and there also are other theories which could explain how life started. So I'm going to stop there. This has been quite a long video, but please do comment if you have any questions, and I look forward to seeing you in the next video.